early stage software startups often prioritize building out more and more technical functionality, and sometimes even when that is at the expense of design concerns like usability or the user experience. And it makes sense why this happens. I mean, so many of the incentives that are driving these startups encourage this. There's just so much pressure on companies to move fast, to scale up, to get bigger, to beat out the competition. But even when companies ignore design at first, sooner or later, they realize that a good user experience is critical to their success, because if people don't like using your product, they don't buy it. And this, of course, is a lesson that Apple has shown us again and again, that design really matters for business, and it matters to a company's bottom line. But when we introduce AI and ML into software tools, we're really changing the stakes here. So when these tools are used to make decisions that affect people's lives, good design starts to matter in a whole different way. And we have to think about design beyond the experience of individual users. We have to start thinking about a wider community of stakeholders and how these stakeholders are affected by the deployment and use of these tools. Because it's not only the benefits of AI that scale, it's also the cost of errors. So assurance auditing is a relatively new type of work for us at IQT Labs. And at the outset of this initiative, a little over a year ago, one of the things that we had to do was figure out, okay, what do we mean by assurance, and how on the earth are we going to actually do an assurance audit? And basically, our starting assumption was this. When it comes to software, one thing we know for sure is that some of the time, some of our tools are going to fail. And AI tools, as useful as they are, they pose some unique modes of failure. Now, recently, I don't know if you all are following literature, but there's been a lot of attention on adversarial attacks. So these are different ways of tricking models into making basically erroneous predictions. And we think of these as intentional failures or malicious attacks. But intentional failures are not the only types of problems that we have to worry about with AI tools. In practice, it turns out that a lot of AI failures or AI incidents are unintentional. So they're the result of engineering mistakes or unintended consequences, maybe an incomplete or a biased training data set, maybe the environment changed, or maybe it's just plain old user error. This could be people using a tool incorrectly or thinking that the results that an analytic tool produces mean something different from what they actually mean. And I think it's really important to remember that a lot of these unintentional failures aren't just about the technology. They're really about how people are interacting with and interfacing with that technology to take some kind of action, to do something in the world that has an impact on someone else. So one of the first things that we did was collect a relatively small data set of example AI incidents. And we were focusing specifically on incidents that were covered in the public news media. Basically, we did this because we wanted to learn more about some of the different ways that AI tools can fail, and we wanted to have some empirical data to look at to help us understand what types of incidents and AI failures might we be able to prevent if we had the right tools and testing. And to me, one thing that really stood out in this small study was that 95% of the incidents we came across were due to unintentional failures. So not malicious attacks, but oversights and mistakes, basically due to either a lack of testing or poor design. And this is just a few examples of the types of incidents that we were collecting. You know, we saw a lot of incidents where a model wasn't properly validated, or maybe it found a relationship between irrelevant features in the data. Maybe the training data was biased in a way that no one realized. You know, maybe there were important privacy implications that no one considered before the tool was deployed. All sorts of things can go wrong. And again, we basically saw these situations where it just seemed like someone didn't fully think through the consequences of deploying that tool in its current state. So we started to think about what it might look like to run an internal audit of a machine learning or AI tool before it's deployed. And the purpose of this internal audit would be to ask ourselves, what risks can we identify before we deploy the tool? Now, when it comes to assurance, we know we're never going to be able to anticipate all of the different ways that a tool might fail. But we figured surely we can do more to think through certain types of risks before something is deployed in a high-stakes situation. And I think a lot of this really comes down to helping the people who make decisions about these tools, whether that's the people who are buying these tools or deploying them or using them, we want to help them understand different types of uncertainty. Now, as I'm sure you all know, the output of machine learning models is imperfect and incomplete. Models don't give us facts. They make predictions based on a statistical analysis of data that's been collected previously. And these predictions are probabilistic, which means they're always going to be uncertain to some degree. But somehow, even though we know this, it can be surprisingly easy to forget in practice. And I think this is because often machine learning and AI tools, they either downplay this uncertainty or they don't convey it in a way that is useful to people who don't have advanced training in statistics or data science or machine learning. And this is a real problem because understanding this uncertainty is absolutely critical in assessing the reliability of the information that these tools generate. Okay, so with this in mind, we came up with these 3 high-level questions that we set out to answer during our assurance audit. So again, we're focusing on a specific tool, and we're basically asking what modes of failure are likely, what could we do to prevent, mitigate, or prepare for these failure modes, and then maybe most importantly, is what we're getting out of this tool what we think we're getting. Another way that I think about this is, how can we run an assurance audit that helps people understand the limitations of a tool? Okay, so how did we actually do this? Well, we decided to basically split our audit into 4 sections, each of which was focused on a different aspect of the FakeFinder tool. This is the tool that we were auditing. So to do that, we did kind of 4 different sub-audits. The first was we did an ethics assessment. And for this, we examined the use case and really the whole workflow around the FakeFinder tool. We did a security audit where we looked at FakeFinder's underlying infrastructure and the software implementation. Then we worked with an outside firm called BNH.ai to run a battery of bias tests. And these were focused on FakeFinder's underlying models and the data that was used to train them. And then we did a design review of FakeFinder's user interface. And for each of these aspects of the audit, we used a document called the AI Ethics Framework for the Intelligence Community. This gave us a set of guiding questions to kind of try to answer through the work that we were doing in the audit. And I want to be clear here, the reason that we focused on these 4 topics was basically because we only had 3 months to run the audit. And we know that there are a lot of other things we could have looked at and could have considered, but we were just trying to prioritize our efforts since we had limited time and resources. Okay, so before I go into what we found over the course of the audit, it's probably helpful if I give you a bit of an overview of FakeFinder, which is the tool that we were looking at. So FakeFinder is an open source deepfake detection tool. And the purpose of the tool is to help users determine whether or not a video is a deepfake. So by this, we mean whether the video has been modified or manipulated by a deep learning model. Now, FakeFinder was developed by another team at IQT Labs, and it was released to open source last year. So if you're curious about deepfakes and you want to try it out, there's a link to the GitHub repo at the bottom of this slide. Now, I keep talking about FakeFinder as one tool, but it's actually composed of 6 different deepfake detection models. And these models were essentially crowdsourced. So we didn't develop them at IQT Labs. One model was the top performer at a competition called the Deeper Forensics Challenge, and the others were the top 5 performers at a different competition called the Deepfake Detection Challenge, which was run by Facebook. That competition launched in December of 2019. Then, in addition to these underlying deepfake detector models, there are a couple of other important components of the FakeFinder tool. So there's a front-end application. This was built with Plotly's Dash framework. And this application aggregates predictions from the different detector models and displays them to users in a visual interface. There's also an API that enables programmatic access to the model output. And then FakeFinder also has a containerized backend infrastructure that helps you spin up compute resources on AWS. Okay, so now for the actual audit. So I'm going to start by talking about the ethics assessment. And the reason I'm starting here is because this kind of contextualizes a lot of the other work that we did in the audit. So to do this ethics assessment, we used an approach called an ethical matrix to help us think through potential concerns. And this is an approach that we borrowed from Kathy O'Neill and Hannah Gunn, and it's described in a book chapter that they wrote that's called Near-Term Artificial Intelligence and Ethical Matrix. And basically, this is a thought exercise that helps people without formal training in ethics, like myself and my team, to think about how an AI tool might impact different groups of stakeholders in different ways. So the way you do this thought experiment or this thought exercise is first you identify different stakeholder groups who might be affected by the tool. These become the rows of your matrix. Then there are 3 columns for each of 3 ethical concepts: autonomy, well-being, and justice or fairness. And then the idea of the exercise is to think through how each stakeholder group might be impacted with regards to each concept. And basically what we decided to do here is to fill out this matrix, or we actually made a couple different versions of it through having a series of discussions with different stakeholders. And so you can kind of look at the matrices we produced as artifacts of those conversations. So the first thing we did was we interviewed FakeFinder's development team about their design goals, and we talked to them about who they viewed as important stakeholders and also the risks that they considered while they were developing FakeFinder. And the primary risks we identified here in this first version are highlighted in red. I'm not sure if you can read it on this chart, but basically we thought there was a potential concern with how FakeFinder defined a deepfake. Or rather, we thought there was a potential concern that if users didn't understand how a deepfake was defined, then it would be hard for them to know how to act on the information. And then the second main ethical concern that came out of this initial exercise was the potential for differential or even discriminatory outcomes from the tool. So basically, FakeFinder's detector models were trained on videos of human subjects. We knew this already. And so if the training data wasn't curated properly, we thought, there was potential to end up with a situation where the models learned some erroneous association between the characteristics of the subjects in the videos, like their appearance, and whether or not a video was a fake. So this is problematic for a lot of different reasons. And we wanted to kind of look into that a little bit more in the audit. So we took this initial version of the matrix and we had several additional conversations with outside experts. We talked to people who specialize in ethical AI, in mis and disinformation, designers of other systems. Like we kind of had a whole range of conversations. And so through this, we identified some additional stakeholder groups that we hadn't thought about, namely video producers. We hadn't really considered them in our preliminary analysis. And we decided to make another version of the ethical matrix, but this time focused on false negatives and false positives. So here we still are thinking about different stakeholder groups, but we're really asking ourselves, what is the cost of an error for each of these different stakeholders? For example, a lot of the people that we work with at IQT Labs are in the intelligence community. So if you imagine an intelligence analyst using FakeFinder, that person might be worried about false negatives. So if the tool tells you that a fake video is real, that could be a problem. But in other cases, a false positive could also be problematic. So if a real video was erroneously labeled fake and then some action was taken based on that, this could lead to videos being taken off a site or censored unnecessarily. It could potentially lead to reputational harm. And when we were doing this analysis, we even realized that there may be some downsides to true positives. So if the tool was kind of supplemented by a policy that was too restrictive around what happened on the basis of a determination about whether video was fake or not, this could lead you to ignore or to censor content unnecessarily. And basically, the reason that we were thinking about this was like, if we think about the perspective of a video producer, there's all kinds of reasons why you might create a fake video that isn't necessarily harmful, right? So I think this exercise was really helpful in kind of encouraging us to think about stakeholders that we hadn't previously considered, and also just think about different risks that maybe weren't initially obvious to us. And this gave us a lot of good direction on what we should focus on for the rest of the audit. Okay, so the second portion of the audit that I'll talk about was our cybersecurity investigation or inquiry. So basically, to do this, we stood up our own instance of FakeFinder, and we followed to the letter the configuration instructions in the public repository. Then for each component of the FakeFinder tool and the underlying models, we looked at third-party software dependencies. And then we built this visualization to help us analyze these dependencies. And this has kind of become a whole separate effort that we're working on, but we're thinking of this as like a nutrition label for open source software. And what we found from this analysis is that it turns out that FakeFinder's models have direct dependencies on more than 90 different software packages. And we're not even looking at, like deeper layers of dependencies. So this is already a lot of different packages. And then even more interestingly, we discovered that one detector model in particular had substantially more dependencies than the others. So that's kind of what you're seeing in this image by the blue dots. It's showing you that like this WN model, which we've encoded in blue, has like all of these dependencies that the other models don't. So this isn't necessarily a problem, but it does mean that this model has a significantly larger attack surface than the other models. And so the recommendation that we made in our audit report was that probably some additional analysis of this detector model should be done to better understand both the nature of these dependencies and kind of the business value of including this detector model. So we figured that this detector model, because of the increased attack surface, it really needed to add significant value to the output of the tool. Then in parallel, my colleague Ryan Ashley did a different kind of cybersecurity inquiry where he basically cross-referenced each of FakeFinder's dependencies with the CVE database to search for known vulnerabilities in these packages. And then he tested several of these vulnerabilities to see where he could develop exploits. And he found a bunch of ways to kind of exploit FakeFinder, including this pretty significant attack vector through something called the WorkZug debug console. So if you want to read about the details of this exploit, I'll put a link to the full audit report in the last slide. So I'll show that at the end of the presentation, and also you'll have that. But basically, the takeaway here is that this exploit enabled him to gain access to FakeFinder's underlying detector models and modify their weights. So you can imagine how that would be pretty dangerous for a user / fun for someone doing this kind of, exploitation. Okay, so for the bias portion of our audit, here we collaborated with a law firm called BNH.ai that does liability assessment for AI tools. And the big idea with this testing was to investigate this risk that we identified during the ethics assessment. So since FakeFinder's detector models were trained on videos of human subjects, we really wanted to know if they exhibited any bias, particularly with respect to protected classes like race and gender. So this portion of the audit basically involved adding demographic labels to a subset of the deepfake detection challenge dataset, and then conducting a battery of different bias tests on each of the detector models separately. And in terms of metrics, here were the 3 things that we looked at to test for bias. So something called adverse impact ratio. This is the rate at which faces in protected groups are detected as fakes compared to faces in a control group. And for the control groups, in this case, we used white and male. We tested for race and gender differences separately. We also looked at differential validity, which is basically like a comparison of system performance by protected class. And then we looked at statistical significance. So this basically involved conducting t-tests to look at the differences in system outcomes across protected and control groups. And in this case, we were looking at true positive scores specifically. Again, the full results of this testing are available in our public report. But basically, the results of these bias tests weren't terrible, but they weren't great either. Basically, we saw that when the models were correct in the prediction that they made, there was pretty good balance across all the classes that we tested for. But when the models were wrong, there was some kind of concerning bias. So for example, I'm just showing results from one detector model right in this slide. With this detector model, we found that for a video that included a subject with an East Asian face, there was, we found that in this case, the model was 6 times as likely to produce a false positive than for a video with a white face. So that's a pretty big difference based on the apparent demographic information of the video subject, which obviously has no bearing on whether a video is fake or not. And so this is the type of difference that really should be addressed before the tool is used in practice. Okay, so the final portion of our audit had to do with the user experience of FakeFinder. But before I get into this final portion of the audit, which was basically doing a design review, I want to give you a bit of background. And just in case some of the terms that I'm using are unfamiliar, I thought it might be helpful to start with a couple definitions, like UX. So these images I'm actually borrowing from Ed Lee, who's a product designer, and he has a really nice way of using serial in order to distinguish between the user interface or UI and the user experience or UX of a product. So if we imagine for a moment that serial is the product we're talking about, then we can think of the spoon as the interface. This is the mechanism through which we're accessing and consuming the product. Whereas the UX, the user experience, is like the entire experience of eating cereal. And there's a lot more to the experience of eating than just the spoon that you're using. So I've also heard UX described as the perception left in someone's mind following their interaction with a tool, or alternatively, the way that people make sense of or find value in the technology that they're using. Okay, so this may sound a little vague, but this is an area that we've spent a lot of time thinking about at IQT Labs, specifically the user experience of AI and AI tools. And in that work, we've designed a lot of interfaces to help people make sense of machine-generated data. And we've also run a lot of empirical experiments to study how people interpret data when it is presented to them in different ways. And again, we do all of this work because we're very interested in how we can leverage design to help people understand and use the output of AI and ML models more effectively. Okay, and a lot of the work that we've done has to do with data visualization. So we're interested in using visualization and visual interfaces to help communicate model output. And we've kind of looked at that specifically because we think there's a lot of potential to use visualizations, particularly to help people without a background in machine learning or data science or statistics to kind of understand and grok what's in this data. So visualizations are really useful. They can summarize large amounts of data in a single image. They can help people see patterns and understand trends. But there's also kind of a catch here because today's visualization tools don't provide a lot of different options for visualizing uncertain data. So in most tools and packages, it's very straightforward to say, add error bars to a bar chart. But if you're dealing with a different type of uncertainty, for example, what category some element belongs to, it's not always so obvious how to represent that visually. And so in our previous work in the labs, we've done a lot of user research and design prototyping in this space, developing and then testing different tools to look at different types of uncertainty. And through this, we've interviewed hundreds of stakeholders, we've built dozens of tools, and like I said, we've run quite a few empirical experiments to try to collect some data about how people respond to information when it's visualized in different ways. Now, in most of the experiments that we run, which we call user studies, we use Amazon's Mechanical Turk to recruit participants, so we can kind of run these experiments at scale. And basically what we're doing in each of these studies is we're showing groups of people different versions of an interface, and then we ask them to perform some task, like retrieving a piece of information or making a judgment. And then we collect data about how well they do on the test or on the task. And we think this is important because it gives us a rigorous way to compare the utility of different visual interfaces, basically by trying to quantify their effect on participants' performance on the task. Now, when we first started doing this type of work, it wasn't exactly straightforward what to measure, like how to measure the utility of an interface. Turns out that was a bit of a research project in itself. So I just wanted to say a few words about that. So one thing that we measure in our user study experiments is something called cognitive load. And this is you can think of this as a proxy for usability. So cognitive load is basically how easy or how difficult it is for people to perform a task using the interface. And the basic idea here is that a well-designed interface should be intuitive to the people using the tool. It should be clear to people how to do whatever it is they're trying to do. And on this slide, I'm trying to give you a very concrete example here. So here you can see a picture of two doors with two different types of handles. And if you wanted to open the door on the left, you would know to pull on the handle to open the door. Whereas if you wanted to open the door on the right, you'd push on the plate, right? You don't even really have to think about it. Just by looking at the door, you know how to interact with it. And this is because the form or the shape of the door handle is designed in a way that clearly reflects its function. It's also why Donald Norman, in his book, The Design of Everyday Things, writes, if a door handle needs a sign, then its design is probably faulty. Okay, so we know that ease of use or usability is very important in the design of interfaces for analytic tools. But it's not enough. It's not enough just to ask people what they like or to ask people which interfaces are easiest or most comfortable for them to use. And here's an example of why that's not enough. So this is a visualization that appeared in the New York Times under the title, Flight of Refugees Around the Globe. What we're looking at here is a map where each arc shown on the map represents a movement of refugees from one end of the arc to the other. And when you look at this map, it's very easy to see that the flight of refugees around the globe is essentially a race to Europe. The only problem is that that conclusion isn't at all supported by the data that's used to make this chart. So in this map, the red arcs or the flows aren't weighted. So 1,000 people traveling from city A to city B are drawn exactly the same way as 1 million people traveling from city C to city D. And as it turns out, if you just look at the data set that was used to make this map, the data actually reflects far more refugees traveling within Africa than into Europe. But that's just not what we see when we look at this image. And so the lesson here is that with data visualizations, sometimes the design, the interface can look really good. It can seem very clear, and it can make the data look as if the conclusions are very easy to interpret. But we still have to do a little bit more testing to make sure that the visuals aren't making it easy for us to draw the wrong conclusions about the underlying data. And this is why, in addition to cognitive load, which we think of as a proxy for usability, we also measure people's performance and the accuracy of that performance on specific analytic tasks when we do our studies. And then third, we're also interested in measuring the confidence or the conviction that people express about their performance. And we look at this because this is like a less quantifiable metric, but we're still interested in this because basically we don't want users to be more certain about their conclusions than the data supports. This is a position, I suppose, that we've taken, but we think that when analyzing data, it's better to know that you don't know the answer than to be overconfident and incorrect. Okay, so we've run all these different experiments, over several different projects, looking at several different tools and interface types. And I just want to share with you two things that we've seen happen over and over again. One is that when people see a visual interface that does not explicitly show uncertainty, most tend to treat the data as if it's certain. So in our experiments, we've seen this over and over again, even when we tell people participating in the study that the data they're looking at is uncertain. It just seems like when that uncertainty isn't shown visually, people consistently report a very high degree of confidence, as if the data they see carries more rhetorical weight than whatever we tell them about the data. And we think what's going on here is that this is an example of a cognitive bias that Daniel Kahneman and Amos Tversky called "what you see is all there is." And this is an unfortunate tendency that many, maybe most of us have, to overlook or discount information that isn't right in front of us. But unfortunately, we've also seen this. So finding number 2 is that when people see an interface that does include uncertainty, many of them actually perform worse on the analytical tasks that we give them. So as you might imagine, this is not exactly what we hoped to find when we started doing this work. And oftentimes it seems like the more uncertainty is exposed through the interface, and by that I mean the more accurately and thoroughly existing ambiguities in the data are detailed, this leads to like worse and worse performance. And so I think what's going on here is that basically when we give people this additional information about likely errors and things that could go wrong, it's very easy to overwhelm and confuse users. Because all of this additional information can kind of distract from the specific information that they're looking for or that they need to do whatever it is they're trying to do with the tool. So basically, it seems like in the design of interfaces for AI tools, we're often faced with this dilemma. We've got to negotiate between, potential overconfidence on the one hand and the potential to kind of confuse, frustrate users and lead to poor performance on the other. And so this dilemma or this trade-off is always top of mind for us when we're evaluating the user experience of AI and ML tools. Okay, so all of this brings us back to the UX portion of our audit, where we looked at how FakeFinder's results are presented to users, and we examined how the interface equips them to act on that information. And this is just a brief summary of the steps that we took in this design review. We basically started by talking with the FakeFinder team about their intended user, and we were also interested in kind of understanding what user research they had done. So how well did they empathize with and how well did they understand the user of the tool? And then we did an analysis of the interface, looking specifically at gaps between the development team's design goals and what's actually being shown in the interface. And we easily could have extended this analysis even further by running a controlled experiment. But we decided not to do that in this case, one, because of time constraints on the audit, but two, because we actually had pretty clear and compelling insights and findings from our qualitative analysis. But again, there's definitely potential to kind of back those up with empirical data by running a controlled experiment. So the biggest concern that we found had to do with FakeFinder's implicit definition of what constitutes a deepfake. So as it turns out, the deepfake detection challenge dataset that Facebook released, and this is what was used to train all of FakeFinder's detector models. Basically, all of the examples of manipulated videos in this dataset had been altered using a specific technique called face swap. So this is a deepfake creation technique where essentially the face of one person is transposed onto the body or the actions of another person. So, and we didn't really understand this until we did like a pretty, we did like a full analysis, and we actually created a data sheet of the data set that Facebook had released. But basically what this means is that all of the different detector models, even though they were produced by tons of different teams at different universities and individuals all over the globe, all the models were really only trained to detect one type of deepfake, this face swap. But Facebook didn't disclose this at the outset of the competition. Now, we know that the test set that Facebook used to judge the competition did include other types of deepfakes, and we suspect that this is because they were interested in the generalizability of models, but they also never released that test set publicly. So it's impossible for us to know exactly what that test set contained. And so the risk here is that we really have no idea how well these detector models perform in terms of identifying other types of video manipulations, really anything other than face swap. So basically what I'm saying is that FakeFinder isn't really a deepfake detection tool. It's a face swap detection tool. And this isn't necessarily a deal breaker. I mean, it's still really great at doing that. But I think that the problem here is that limitation needs to be clearly disclosed to the people using the tool. But at the time that we did this audit, there was nothing in the interface design or in the FakeFinder documentation that explained this constraint or this limitation of the tool. And we thought that this was a really significant issue. Basically, if FakeFinder's users didn't understand that not fake really only meant not face swap, there's all kinds of ways that you can anticipate or you can think through how they might misuse the results of the tool. Okay, so I've covered a lot of ground already in this talk, but I just want to end with a couple of slides about designing human-centered AI. And that's because I think this is the best way to avoid these types of cognitive errors or this mismatch between what a tool does and what users think the tool does. So I think far too often when we're developing new AI and ML capabilities, basically the emphasis is on training a bunch of models and maximizing the predictive accuracy of those models. Then we build a bunch of tools using those models, and we hope that people will adapt to them. And I think what we need to do is get better at making tools that meet people where they are. And these tools need to help users understand the limitations of these capabilities. And I think to do this, we have to show people the types of uncertainty that are relevant to the specific questions they're asking of the data. But we have to do this in a way that doesn't overwhelm them with unnecessary complexity or obtuse technical jargon. And so my recommendation for how to do this is to begin with an understanding of the people who are going to use the tools, then to design the model and the interface, or the models and the interface in parallel. And I think this is the best way to give users the information that they actually care about. And the reason to design the interface and the model in parallel is that feedback that you get on the interface or decisions that you make about what information to expose can actually help you make sure that the models you're using have the right features. So you want to make sure that you're making predictions about the right things in the way that you design those models. And then finally, I think we need to evaluate emerging AI and ML capabilities based on the utility that they provide to actual people. And when I say this, I think it sounds obvious, but this is just not what we always do in the tech community. Too often, predictive accuracy is the only metric that's looked at. But I think for these tools to really be useful, we have to think about utility a lot more broadly than that. Okay, so hopefully I've given you a sense of why we think that UX design is an important aspect of AI assurance. Basically, if we want to prevent AI incidents, we have to think about how real people are actually going to use these tools and how they might potentially misuse them in real situations. And I want to leave you with these 4 recommendations that come from a human-centered design approach. So these are things to consider when you're building or buying or using or auditing AI and ML tools. So 1, people need to understand the limitations of the tools they use. I think this is the only way for us to assess risk and ensure reliability. 2, I think designing a model and an interface in parallel can help us ensure that these tools provide real value. We can use people's feedback on the interface to help identify the most important model features. 3, when it comes to interface design, I just cannot emphasize enough how important it is to keep things simple. And then 4, we need to use human-centered metrics that help us evaluate AI and ML tools based on the utility that they provide. So to think about, again, how these tools are going to be used by actual people in a real scenario, and not just think about accuracy kind of in a vacuum. So that's all I have for today. And then, like I said, I have a couple of links here to the public version of our audit report, to the FakeFinder code repo if you want to try that out for yourself. And then we also have published several posts about our assurance audit of FakeFinder on the IQT blog. This is just a link to the first post, and you can find the others from there. And I'll make these slides available to everyone. And this is my email address if anybody wants to get in touch or has any further questions.
Thank you so much for this wonderful presentation, Andrea. This has been very enlightening. I have a bunch of questions, and I know people are typing in some questions online, so please feel free to do so. I'll start with some of my questions so that we can start the discussion, and then I'll take some questions from the audience too. So first of all, one of the design challenges we have is how much of decision-making are we delegating to these models, right? So are we using models as a way of basically replacing human decision-making versus using models to support human decision-making, right? So, in the context of, let's say we are automating certain things, and in an autonomous driving setting, if you will, we are expecting that these models take decisions on our behalf because they are making decisions based on the information being presented to them. And if we are using, let's say, a tool which we are trying to figure out, how confident is the model saying that this is a fake record, or the applicant who is applying for a loan is potentially a fraudulent user, or if we are trying to figure out, and in this particular use case, is an image a fake image or not, right? So how do you kind of position the design requirements for these kinds of use cases when the audience could be potentially the machine having to make a decision wherein you're only focusing on outcomes from the model versus humans who are going to now kind of look at it as a potential, you have your own decision-making framework, and you're using this as just one additional parameter when you're making decisions?
Yeah, great question. So I don't think there's any like one answer for this. I think the way that I think about it is that I try to think about it in terms of the cost of something going wrong, like the potential cost of something going wrong. So, and then the higher the cost of an error, the more either you want to minimize the chance of failure, or if you can't do that for some reason, because there's things that you can't know about the world, so you don't trust your prediction mechanism completely, then you want to have some oversight mechanism. So to give a few examples, I use email, and that email client has a spam filter, and I don't know exactly what type of model is being used to make a determination about whether inbound emails are spam or not spam, but I'm sure that's done in an automated way. If that model makes an error and misclassifies, a spam email as something that should go in my inbox, the cost of that error is very low, right? Like maybe if I get a lot of spam, I get a little bit annoyed. I guess the worst thing that could happen is I get so annoyed that I switch to a different email client, but like the cost of that misclassification is very, very low. When we talk about autonomous vehicles, obviously the cost is much different. I mean, there's human safety potentially on the line. So a vehicle that misclassifies a person as not a person, like a pedestrian as not a pedestrian, and then ends up hitting and harming that person, obviously the cost is a lot higher. So if it were me responsible for making a decision about when is that AI ready for deployment, I would say, it makes sense to have to kind of, it's okay to like have a slightly higher risk tolerance when the cost of an error is a lot lower.
Yeah, that's a great point. I'm trying to like look at this from the angle of formulating an audit. And thanks for presenting, the framework you used and also the key attributes of an audit. So when I kind of look at it holistically, like, okay, so what does it mean to do an algorithmic audit? And many times it's usually use case driven. Like, are we trying to just look at bias, and is the model going to be making certain decisions which could potentially harm a particular community or particular set of users? But you kind of had like multiple facets like security, bias, and other additional things. So the question is, how would the community kind of, especially in an industry setting, start building out frameworks wherein you can look at it comprehensively? Should it be like top down, wherein we are going to say, here are all the potential things we could do in terms of looking at a model, slicing and dicing, quantifying various aspects, and then gravitating towards what makes sense for a particular model before it's deployed in production, or looking at it from a use case perspective. So here are the users, and this is their, maybe training, because they're not, statisticians or, data scientists, but they're going to be end users, just basically picking between 2 or 3 options, versus a highly sophisticated training machine learning professional who can potentially, look at the graphics and look at the dashboards and make more, high quality decisions, if you will. So how do we kind of, formulate the audit? Is this top down versus bottom up? I don't know if you have any ideas there.
Yeah, I think this is a great question. I think this is like the big question about auditing. Yeah, I'm trying to think. I don't, I definitely don't have like the answer for this. There are, over the course of an audit, like if we're trying to identify risks, there are so many different aspects that should be considered, or could be considered. But at the same time, for any organization looking to deploy a tool, like if the auditing process is sufficiently arduous, then that's an issue too, right? I mean, nobody has unlimited resources to audit models, especially when you're thinking about a scenario where an organization might be using hundreds or thousands of different models. Like there's just a limit pragmatically on what you can realistically do. And I think it would be a real shame to kind of make the expectations so onerous that it's a deterrent for experimenting with new technology. Like that's certainly not what we're trying to do in our assurance work. But I think finding that balance is really, really difficult. And I wish I had all the answers for like, oh, here are the most important things to look at. I think this is why I started the presentation with the ethics assessment, because I don't know if that's the best way to go about it, but we found it very helpful to kind of think about the tool and the use case at a very high level, to kind of think about like, okay, what seem like the most significant risks here, and then to make sure that we cover those in the audit. Now that's not sufficient, but that was something that was helpful for us in kind of prioritizing the limited resources and time that we had to conduct the audit. But I think also, I mean, I'm optimistic that as algorithmic auditing matures as a practice, that there will also be like more tools and platforms available that can help kind of standardize and automate aspects of this so that we don't have to do everything so manually for every audit. I mean, that seems completely unsustainable going forward.
Absolutely. Absolutely. And again,
but
yeah, I mean, and again, that was more of an open thought, discussion question rather than, having gravitating to an answer, because that's the dilemma I face too. Yeah, when we're working with clients, just formulating. So what would you recommend as an algorithmic audit? So, well, here's all the things we could potentially do, but what makes sense? What adds value? And as you were kind of mentioning, what's the most risky aspect of your model? What could potentially go wrong if something bad happens with respect to the model? So maybe start from there and then kind of, go back and figure out like what makes sense to make it pragmatic. Now, I think,
oh, sorry, go ahead.
No.
I think a lot of this comes down to the individual, the risk tolerance of different organizations, right? And that also, in addition to like the models are going to vary, the use cases vary, the cost of errors varies, but the other thing that's really different is like different organizations are willing to or are able to tolerate like very different amounts of risk, right? And that depends on the type of organization it is and what their function is. And so I think that's also important here. So yeah, I think that kind of high level analysis can maybe help initially to just identify, okay, like what are like the things that are like existential risks for this tool or this piece of technology? Let's make sure we think about those. Then like, what's the next, if we have additional resources, let's prioritize like, what are the like maybe not catastrophic risks, but could still be really bad, like could still cause significant reputational harm or significant, like cost due to lawsuits going forward or whatever. And maybe that's a way of kind of prioritizing the audit activities. I'm not really sure.
Yeah, I mean, one of the things we are trying to work out in the course we teach is basically, start looking at it holistically as an audit design question, wherein you basically look at all the facets, because it may or may not be relevant, but you ask the question whether a security audit makes sense or whether it makes sense to look at the data aspects of it. You have control of the data in the first place. If you do not have control, then there's no point in trying to just go and just looking at the data. What should you be doing from a pipeline perspective? What should you be doing from an explainability perspective? What should you be doing from a fairness perspective? security, as you mentioned. So kind of doing that high-level assessment to design the audit questions in the first place. And then you mentioned the metrics, right? So because how are we going to evaluate whether what the outcomes are good enough for deployment, right? So some of it you had a whole paper, and I didn't really get a chance to read it, but you talked about the quantification metrics for the visualization aspects, right? And that kind of quantification is necessary in various aspects. There are so many explainability metrics at this point. There are so many fairness metrics at this point. So what makes sense in what context, right? Yeah. The context drives the metrics rather than the other way around. And then the third aspect becomes how much, and that would be determined by the risk, as you mentioned, which is, how critical is the scenario. And that also leads to the test design question, like how many tests should we be doing? What should be the suite of potential tests? Are we going to only look at historical findings, or are we going to create new tests of like the unknown unknowns? Like we have never seen those scenarios before, but we want to even try it just to figure out whether how will the model perform, so that we know what kinds of barricades we can draw. So I think the analogy is probably we're kind of doing something similar when the automobiles started coming in, right? So we had these processes which people were figuring out, like, is this vehicle road ready? And then when it's started becoming a question of scale and automation, they had to basically formulate ways in which you could standardize the production of parts, production of processes. I think we are kind of dealing with similar analogy in here in terms of machine learning process, and it'll be an interesting thing. Then I think we probably have like time for one question. I think Jamie had a question about, how do your clients view and adopt audit findings? Is it more of a collaborative process, or is this more of another additional data point when they make decisions? So how do your clients for this particular audit think about viewing and adopting these findings?
How do they think about viewing and adopting the audit findings?
The audit findings, yeah.
Good question. So I would say for the auditing work we've done so far, we've kind of been working with two different types of partners. So we have some partners in the government who are interested in the specific findings. There's definitely more we could do to kind of document the findings in a standardized way. Like we're just at the start of figuring out how to do all of this. So I think in the case of our FakeFinder audit, basically what we did is we took the audit report, we sent it to some folks who were interested. We sent it back to the FakeFinder team. We told them to fix some stuff. That was easy for us to do because it was like an IQT Labs team. So we basically said, hey, we're publishing this report that like identifies some issues with your tool. You may want to fix those issues. And then we actually helped them fix like several of like Ryan, my colleague who did the cyber work, he like fixed a lot of the exploits that he sort of prevented a lot of, changed the code base to prevent a lot of the exploits that he had discovered. But some of the partners that we're working with in the US government are more interested in, like in addition to the specific findings, they're more interested in like our recommendations about auditing methodologies and tools. So, to help support them, what we tried to do when we wrote up the audit findings is not just write up the findings, but also be very explicit about like what we did and why we decided to like set up each portion of the audit in the way that we did. And I think it's important for us to like almost over communicate these methodological decisions at this point, because we are not at all sure that we're doing this in the right way or the best way. Like this is very much a like learn by doing kind of experiment. So what we're really trying to do is just create some examples, like unclassified examples of audits of unclassified tools that the government can have access to and use and also share with other partners. But yeah, we don't want to create the impression that we think we have everything figured out, because we absolutely don't. So we're just trying to share what we did and then also be very like critical and reflective of our own practice. So we say, here's what we did, here's what we found. And oh, by the way, here are all the things that we think we could have done better, but we didn't know that at the outset. Like here, like we know, for example, that most of the things that we did like are just not scalable because everything was so manual. Like even all the technical testing that we did, it was just all manually done. Like we completely understand that that is not sustainable or scalable. But we also feel like we're not at a point where we know how to automate some of these things because we like don't know what to do yet. So it's very hard and dangerous to like try to automate something before you really understand what you want to do. Because then you're just making a bad process faster. We don't want to do that.
Absolutely. And again, it's an evolving field. We'll probably hear a lot more conferences, a lot more, academic papers and practitioner notes kind of coming out, which will, start adding more robustness to the process aspect and also kind of having the specialization aspects. So for these kinds of models, this makes sense. For these kinds of models, these other things make sense. But this was a fascinating discussion, Andrea. Thanks for taking time out of your busy schedule and making time for us. Really enjoyed the discussion. And I will share the slides with the audience. And I will also share the video once the recording is up and running. And we will continue the discussion online. Thank you so much again.
Wonderful. Thanks again for having me.
Thank you.